now introduce Carlos de Andrea from Barcelona, who will tell us some more about elimination theory.
All right, thanks a lot. I don't know if you listen to me. In general, I speak faster. Can you hear me well? Well, thanks for, it's a pleasure and honor to be here and to continue talking about elimination theory. But before that, just let me do some announcement. This is working. Yeah, before we start, just don't forget that we have the session on open problems Friday at 3:30. So this is how it's going to work. We're going to gather here, and I mean, you're going to bring your own problem. So it's not that we're going to provide for them your own math problem, but we're planning to schedule like 5 minutes per presentation. So this is going to be first come, first serve. So I mean, if we have a lot, so you might as well book a time slot as soon as possible. Just talk to either Hal or me, or send me an email. I mean, each of us will have 5 minutes, and you can, I mean, share with all of us. I already was told that there's not going to be any recording, and probably we won't talk about those problems after we leave the room. So don't be shy and bring your problems. It would be fun.
So maybe we say one other thing about it, which is that so if you're working on a thesis problem, this is not the place to present your thesis problem.
Yeah, probably not.
But the idea is to use this as an opportunity to start some collaborations going, right? So if you have something that's been, worrying you for a long time, but you never really felt like actually spending the investment of time to solve the thing, but you think, hey, maybe there's somebody who would be interested in it, then that's a good place to publicize it. And a great way, I think, for these 5-minute presentations to work is if you just give really one short turbo example, if you can, shoehorn that into 5 minutes, and then say what the problem is. So something that sort of grips people's attention.
I think that's going to happen in this room, so you will have all this technology, like this Blackboard, and which we haven't used that much yet, but also this. But I mean, we want to listen as much as possible, so I mean, that's why we need like 5 minutes and also prepare it well. And just send an email or just come and talk to us, we either Hal or me, and it will be fun. Okay, so I was being asked to talk about elimination in the 21st century, and well, after thinking for a while what I want to say there, so I was thinking, well, I mean, what are we dealing now in the 21st century that essentially is making us all marching towards that? Well, I mean, apart from being crazy about applications, and this conference is about that, so I mean, this is something that is kind of new, and this is why, for instance, all these polynomial systems are getting a bit more in fashion because of the applications, also the implementations of the algorithms and the things that we got. There is something that is triggering all of us, and it's very, not only in math, but in everyday life, which is this thing. We really want things to be done, and we want them now. I mean, you think for a while, I mean, now we want a car, and we want it now, so that's why we use Uber. And I say, yeah, this is a very beautiful equation, but I want to see the point of your variety, I want the dimension, and I want it now. So, and this is something that is important. I mean, you might think that probably, I mean, yeah. But it's essentially leading all our computations and all the things that we're doing in that direction, in how to compute things, how to make things computable, right? The problem in elimination is that it comes at a cost, at a theoretical and also as a practical cost. And I imagine that pretty much everyone here in this room has dealt with that at some point. So let me show you a bit, which is the theoretical cost that, I mean, to solve a system or something. In principle, you have like some equations. Let's say I have n equations, n unknown. This is a square system, so I expect to have a finite number of solutions. And then I want to put all this in a computer, right? So then I need to know the size. So then, I mean, the size of a system, which is for, I mean, I want to quantify a bit the size. Let's say the size for me, I'm going to measure the size as kind of the degree of these polynomials. And also this L is going to be the size of the coefficients. I mean, you may think, for instance, the coefficients are integers, and this L is like the number of bits that they have or something. So this is like the size, and then let's say I put this in a computer, and then I expect to give me, the final number of solutions if it has, and where they are, and some kind of codification. And what we know is essentially that the size is bounded generically by this d to the n, which is the Bezout bound, but also the arithmetics of the output is bounded also by this number, n d to the n minus 1 L. So what I mean by this is, if let's say if you're lucky and you have a rational number, this is more or less the number of digits that you'll need to codify that thing. Most of the time, you'll have a lot of them, and then you have to compact them somehow. And from a computational point of view, this is bad. This is exponential. So it's not something that computers can do. And moreover, I mean, if you use any kind of elimination, like linear bases that eliminate everything, it's even double exponential. So it's something that is bad. It will take ages to do things, and it's frustrating. And most of us have spent a lot of time with a lot of code trying to compute some examples that didn't work because of this. And this is frustrating, and this is something that is essentially kind of against the fashion, right? So we want to compute things, we want to be able to compute things, we want to compute them fast, and we want to compute them now. So what can we do? This is one option. We can go back to Grothendieck and those abstract algebra that things probably doesn't have complexity or thing. But there are other things that we can do. For instance, we could relax the input. And I'm going to tell you a bit what I mean by relax the input and hope that the output also is going to be relaxed. Another thing that we can do is we can change the computational model. Right? So, I
think that's cheating.
Well, but it's in both cases, I think they're cheating. But
The computational model in particular is cheating because you only have one type of computer to work with these things.
well, but you get to publish papers with those. And also,
Okay, that is also cheating.
yeah, no, but also you get to actually compute things, right? So, you get to compute things. Well, you can think also in the previous things. We have this resultant, which is a beautiful elimination object that theoretically is very well described as a projection, everything, and we have all the tools to compute. But then go and compute one. I mean, go and compute the polynomial resultant with all the parameters and everything. It's impossible. So then, I mean, you have to compromise at some point. You either want something that is theoretically perfect, but impossible to compute, or some approximation of it that actually is good for computations. Okay? So let me. This will go back. So I'm going to explain a bit more what these two things are. So relaxing the input, for instance, this is something that is going to appear. Tropical geometry, and this is, something that you, instead of looking at your rigid variety, you're actually looking at something simpler, but you can actually compute things. And you can actually compute things of your original variety. It's not that you invent some other object that is easy to play with, and then it doesn't have anything to do with what you wanted. It actually gives you a lot of responses, and gives you a lot of information about the original object you were trying to compute with your classical approach. Another things are these relaxed resultants. I mean, David mentioned some of them today under the name of sparse, for instance, but there is a huge zoo of them. That also, I mean, instead of codifying the thing with a lot of monomials, you just get less information, you put less information, and hopefully you get less out. You have these implicitization matrices that also they were introduced today by David at the very end, and we'll say a bit about them, and also they will appear also on Wednesday, so I mean, you won't miss that. There are all these usages and Riesz algebras that I'll say a bit about them today, and also on Wednesday you'll hear a lot about them. So this is what I mean by kind of relaxing the input. I mean, it's under the way relaxing there are a lot of things, because for instance you might think that these usages and Riesz algebras, they are very, very complicated, or at least deep objects from commutative algebra, but they actually help you to understand and to simplify in a lot of cases some formulations that in their classic way they were large, and now they can get simpler. Well, and what does it mean changing the model? Well, this is what I mean when I change the model. The probabilistic algorithm.
That's okay.
That's okay. Okay, so yes. Good. So
the real number takes 1 unit of time to compute.
Exactly. Yeah. No. I think at the end of the day we're going to be having a beer together and having fun about it. Another thing is computation over the reals. This is another model, and I mean that works, and it has its own life of its own. Parallelization. So instead of chasing the d to the n roots, you just choose to chase one, and maybe you're lucky, and then the thing doesn't get exponential anymore. But then you have to do it d to the n times, no? But at least in this sense, you may have some hope that the thing can be done. And these homotopy methods that also will appear tomorrow. So But these two things, this is what I mean when I say relaxing, changing the model. I mean, not really invent something else. I mean, this whole thing has been done very well. So, and this is what I'm planning to do today. I hope you ate well, because this is what I plan to do. So this is, I don't know if you know the word tapas, but actually this is what we have in Spain when you go out, actually before having dinner, you go out and eat a bit here, a bit there, and you try a lot of things. So instead of kind of coming here and giving you the insight or where the elimination theory is going to go in this century, which I don't know, I'm going to give you some tapas. I'm going to give you some little pieces of things that we have already seen them happening. They are happening right now, and they have a very promising future. So it's very likely that, at least in the following 20 years, I mean, they're going to be here with us. And I hope that, I mean, some of you can also join us into this adventure. So just some disclaimers. I mean, these are not the highlights of the 21st century, or the 21st century so far, because, I mean, it's not done yet. The century, I mean, and also, and also, I mean, I didn't want to make a list of the highlights. It's just a sample of results. It's like when you go to have tapas, there's no way you can know where you're going to get the best tapas. You're just going to get some. So this, you're going to get some samplings, and also, I mean, all these areas are very active and very promising right now, and I mean, probably several people here in the audience are working on that, and also. More of them will appear in the future, and of those, I mean, I cannot say anything because we don't know yet. So also, a lot of important names and interesting areas will be omitted, so I already asked for forgiveness about that. I'm just going to show you some things that, some pieces of work that have been occurring in the last 10 years, 15 years, and I chose them because I like them. So I hope you can enjoy this tour of tapas with me. I hope you ate well, and I hope, I mean, in any case, there's going to be food quite soon, so don't worry about that. So here we go. Let's start with tropical geometry. So this is the thing that you go from something that is exponential to polynomial. So I don't know if you know about what the tropical variety is, but in principle, I mean, if you make the picture of a variety on complex space, it would be something like this. And then you kind of like use the modulus function on the coordinates and take logarithm, and then you take some kind of limit. And so what you get is a fun. So which is the union of all these lines and things. And this is essentially the tropical variety of V. Okay? I mean, it's probably not well defined, but in principle, this is the idea. You have a complicated algebraic object, and by using some metric that in this, at least in this picture, is the modulus function on the complex numbers, you get a fun in R to the n, and this is a tropical variety of my variety. You can do this, if you can change the modulus function, with that you can change C with some valuation ring, and the modulus function with that valuation, and you get something that may be simpler, more complicated. But this is essentially the tropical variety, and the process of doing this you can call tropicalization. You may think that you go from the world of algebraic geometry to the world of fans. So fans in Rn, and the geometry more closer to the Euclidean geometry there. And it's so important that it has a code on its own in the MathSciNet, in the Math Subject Classification Code of 2010. If you look, in 2000, this code didn't exist. So this 14T didn't exist anymore. So this is one of the things that it appeared now. It's of this century, and it's there, and it's important in its own that it has its own name. And what's a nice feature about this is that computing tropical variety is something fast. I mean, you don't need to do the whole picture of your variety and everything. You just get the equations, you can compute it, and it's fast, and encodes a lot of information about the original variety. So there are a lot of things out that we know and we are able to compute about varieties, degree, dimensions, singularities, and everything, thanks to the fact that we can tropicalize them and we can make a computer do things. So here goes the first tapa. We're going to talk about tropical discriminants. Discriminants are an object also important in elimination, and you probably have, most of us have seen them probably in high school with the discriminant of a quadratic polynomial. And in modern terms, so this is the paper I'm going to talk about. In modern terms, this book of Gelfand, Kapranov, and Selevinsky was about A discriminants. But when you go through the whole book, you learn about resultants and a lot of things. But what you end up with the idea is computing discriminants is very complicated. For instance, it's not even clear until today, given a configuration, whether the discriminant is a hypersurface or not, whether you're going to have one polynomial to define it. And those things, and not to mention formulas to compute it, which are the monomials that appear, how to make these things happen. So they are very hard to compute. But yeah, well, I mean, there's some instances of that problem that have been solved, but yet there are a lot of Cayley configurations that we don't know how to approach them. And the interesting thing of this paper is that they could actually compute the tropical discriminant, and they could do it in a very simple way. So let me show you the main result, which is theorem 1,1. So this is the result. The result says as follows. So I have a matrix, which is the matrix that codifies my whole set of monomials, if you want. And then the result says that the tropical discriminant, which you may think that is a tropicalization of the discriminant, is equal to the Minkowski sum of this Koberman fund and the row space of A. So the row space of a matrix, you can imagine what it is. Well, it's like this. I mean, the Minkowski sum is just you have to make the set of all the elements of here plus here. So it's a very easy to describe object, well, provided that we know what the Koberman fund is, right? So, well, just if you may think that Koberman fund is like the tropicalization of the kernel of a matrix. So this is a very beautiful result because I give you the matrix, you just have to compute the kernel, and then tropicalize it, and then just the tropicalization of the discriminant is going to be the Minkowski sum of these two things. It's a very simple outcome compared to an object that we still don't know a lot of things about it. For instance, thanks to this result, now we know a lot about like the Newton polytope of the discriminant, and also, I mean, the extremal points, and a lot also about this codimension one thing. So this is a very beautiful paper that actually has, I mean, it was kind of new in the century, but actually it triggered a lot of research in that direction. And until today, I mean, it's a very hot area. There's A discriminants and this is the study of singular locus and things like those. So this is the second tab. It's tropical elimination. So I mean, we're talking about elimination. And this is a paper by Bernd Sumpfers and Geneviève Belev. It's called Elimination Theory for Tropical Varieties. And the question that you may have now is, so I have this, the typical problem in elimination. I have this incidence variety I project. And so the question is, what happens if I tropicalize this, and I tropicalize this, and what happens in that situation? So here's the result. No, I'm going back. This is, again, theorem 1.1. So because we are talking about toric varieties here, now you have a morphism of tori, you may think now that this is the space on the top, and this is the one on the bottom. And now every of these morphism, because I have a toric morphism, has a linear map associated to the lattices. And now this is my incidence variety. Suppose that I go from my incidence variety from here to here, and it's finite. I mean, you may think that here, this morphism, this n in general is going to be larger than this, but suppose I have a variety here that goes finitely down there. Well, so then this matrix A induces a generically finite map of tropical varieties from the tropicalization of the incidence to the tropicalization of the image. And again, I mean, we pass from something which is very kind of complicated from a computational point of view to something that is linear algebra. And again, this result that seems like an intellectual game, if you want. I mean, when you look at this, so you think, of course, this is the kind of thing that should be true. Well, not only is not easy to prove, but also came with a lot of consequences for like Newton polytope of the elimination and of the result and things like those.
So in this case, there's two degrees here. There's the degree of the generically from x to alpha x, and then there's this other generically finite degree.
Yes.
Are they the same?
No, not necessarily.
You can imagine roots of unity helping the degree from x to alpha x. They just disappeared.
Yeah.
So do they understand the relation between the degrees?
I didn't go that far in that paper, That's a good question. There should be a connection, definitely.
What's the T on perturbator?
The T is the torus, is this C star to the end.
So it generates a form.
Yeah.
No, there's two T's. There's a black or bold T, and then there's
Okay, well, okay.
Yeah,
Well, this T,
at the end.
okay, this is C to the end, and the other T is the tropicalization of the variety. Yeah. Yes, it's true that I actually copied pretty much the way I should probably have to put also the 2 pages before this statement, but we would get bored by then. Yeah. Well, and then what about tropical resultants? We were doing the tropical discriminant, we were doing tropical elimination. So this is another tapa. This is from a paper, very beautiful paper from Anders Jensen and Josephine Yu, and where they compute tropical resultants. But well, we have to be very careful with this because there is a difference between what is called a tropical resultant here and the tropicalization of the classical resultant, which they are connected. And I'm just going to put some excerpt from the abstract in this case. So here they put the supports of a list of tropical polynomials, and I'm not going to explain to you now what tropical polynomials are, but in principle you think that when you compute logarithms, the product gets converted into addition, and the addition gets converted into some kind of max, right? So these are the operations that you do in the tropical world are instead of product and addition, you do addition and maximum. Then you are not in a ring anymore. There are some issues there, but anyway. But you can build polynomials and stuff, and these tropical polynomials are defined in that sense. Then they define the tropical resultant as the way it seems natural, the set of choices of coefficients such that the tropical polynomials have a common solution. So this is not really the tropicalization of the resultant, at least with that definition, but they get to prove that is the tropicalization of the algebraic variety of solvable systems. So actually, see, you go from one side and you prove this other thing, and this is the important thing. They can be computed in polynomial time. So you can compute, again, again, this is a theoretical result in the sense that there are things that you can compute in polynomial time, like Gauss reduction, but then in practice you cannot do it. So, the fact that you can compute in polynomial time doesn't mean that you can now go home and you can compute all the possible instances of this thing. But it goes from exponential to polynomial, and it's great also, because in this paper also, they get to say a lot of things about Newton polytopes of the classical resultant, the way we used to know it, and also, and they say new things. So this is, they also say something else, that is a new algorithm to recover the Newton polytope from the support of the tropical hypersurface. You see, this is, you go back and forth from something that is, in principle, you think that, well, you're losing a lot of information from your variety or from your surface or whatever, but you actually can do things, you can compute, and it's feasible, it's implementable, and you can do things. Great. So what about relaxed resultants? So David was talking a bit about those today, and the general philosophy is like this, that in the real world, you have polynomial systems that they are not, they don't have all the monomials when you expect some kind of degree, and then you probably want to take a closer look or just keep track of the coefficients that appear there. And this is in the spirit of the sparse resultant that was introduced today, and the thing that we did with Martin Sombra not that long ago, this is the typical diagram that appears always. Elimination, you have this incidence variety. Inside of here, this is the tora, you project, and then you compute the equations, actually, of the closure of the image here. And the only difference between the classical approach and this one that we did with Martin is that instead of taking the equation of the image, it's just the equation of the direct image. In principle, this is kind of silly because the direct image is irreducible, so it's either an irreducible polynomial below that defines the classical resultant, or it comes with some multiplicity. And then what you have to take is that equation with multiplicities. But that silly observation essentially led us to understand how this complexity gets translated into now something different, which is the mixed volume of the Newton polytopes of the support. And that essentially tells you that if this mixed volume is small, then your outcome is going to be small. And this is the kind of the game in this kind of sparse resultants is that, I mean, the smaller your support, but here the thing that smaller, it doesn't really mean very few coefficients. Smaller or small means this mixed volume should be small. And so then you have some chance of having things being easy to compute.
Yeah, so this result, the d to the n goes to the mixed volume, and the d to the n minus 1 goes to the same mixed volume.
Yes, this is because, actually, the thing, because if you think, you have to think for a while that this d to the n codifies a system of n polynomial equations in n variables. And so what you're essentially, I mean, so you don't have n plus 1 like here. So and you should probably have to take like a resultant with hidden variables. And this is where, for instance, this n mixed volume on L appears because of some projection. But yeah, so the complexity of computing the dispersed resultant is also well known, and probably you have to change this n with this n minus 1 with n and this with n plus 1.
So A naught doesn't appear in here.
Yeah, well, again, because you...
It's hidden.
No, well, the thing is, you can think either you put a generic linear form or you project. Yeah, because, I mean, this is kind of, it may sound like confusing because this d to the n didn't appear from solving a system with n plus 1 equations, but with n, right? But, I mean, the way we could actually solve that problem, especially this one, this is well known, this is Bezout. The way we could actually tackle this was by using resultant with either hidden variables or with U resultant to compute the height, for instance, of the solutions. But you know, you could also relax in very different ways, not only look at the track of monomials. I mean, you can just replace, you can do the same game. I mean, I just have to look at these polynomials and look at their zeros inside of some variety. And if you can codify your variety in a very clever way, there's some chance that these equations can also get relaxed, right? And there are a lot of examples that were done even in the last century, even before, actually. Those things that David was presented today with the Bezout thing and also with these cuts and everything, this is another way of codifying things. These reduced resultants that actually the first time I saw them was in a paper by Zariski, and Joan Luth treated them in one of his sequence of papers. Essentially, you start with a system of polynomials that you know that the origin is a solution and with some multiplicity. So in that case, what you did was you replaced the Pn that was there with the blow-up of Pn in a point. That's another variety, and actually there are formulas for that, and in some cases they are very simple formulas, in some cases you have determinantal formulas, and everything is fine. There's also these weighted resultants, where you replace Pn with the weighted Pn, and again, Joan Luth has if you go through the series of his paper, at some point appears a whole thing about these weighted results and the theory, and which is the degree, and which is the, so, and all the things that are done there. They are parametric resultants. They were introduced very recently. And again, instead of parameterizing your system with monomials, you just use some family of functions. Right? So I expand, like for instance, Bernstein functions or whatever functions you want. You use them, and so then you know you have a different representation of your thing, and using that representation, sometimes you are able to produce smaller, more compact matrices. There are some residual resultants that Laurent Bousset worked out in his thesis, where again, here you have your functions, they all belong to some ideal, and this ideal is the residual of a complete intersection, and there are lots of things like this, actually. For instance, there is some determinantal resultants where the variety that you are working on is some kind of determinantal variety. So in that sense, you put a different space, you do the same game of elimination, it will work, the elimination theorem will work, and then if you are lucky and you choose well your space, I mean, you may get, more compact formulas and simpler formulas to do this. What about implicitization matrices? Well, you remember this matrix that was introduced this morning, this is van der Wander, that you essentially have some polynomials, and you write here all the monomials. Here you put all the monomials times these polynomials to some power, to some degree. And here you actually have a matrix where the matrix essentially depends on the coefficients of the polynomials. So this is not, this is not going to be what the implicitization matrix is, but it's going to explain the philosophy. So one of the things that we had was this, that the rank of this matrix drops, as at some point if I leave the degree of all this game, if and only if there is a common solution. And after that, the next thing that appeared was that, well, then I computed the maximal minus of this matrix. And somehow we get comfortable with that idea of computing the maximal minus because we have polynomials, and then and we go old school, right? I need a polynomials, so now I have this system, I want to see the things, whether they have a solution or not. But in principle, I could just stay here and say, well, why don't we just check the rank of this matrix? Why don't we check if it drops or not? I really don't need to do that. If you give me a matrix of numbers, the last thing I'm going to do is going to compute all the maximal minors to check if that thing is 0 or not, right? So why is that we don't do that? So that's the idea of this implicitization matrices, is to change the chip. You have to change the chip. It's hard. And instead of giving a list of polynomials that define something, you just give me a matrix. And the condition on the rank of that matrix is going to tell me something about the geometric object. So in that spirit, this is the TAPA. This is a paper by Laurent Bouzet. It's called Implicit Matrix Representation of Rational Bezier Surfaces, Curves on Surfaces. And this is the idea. So let's say I give you, the paper goes further than that, and you'll hear a lot about this on Wednesday too. But let's say I give you the rational parametrization of a spatial curve. So this curve lives in C3, and the parameter T moves over Z. So what would be the classic implicitization problem here? Well, it's like compute the equations of the image, right? So I'm going to put X equals to this, Y equals to D, and Z equals to D, and I try to eliminate T, and that will give me some equations. And those will be the equations of the image, which is the 21st century implicitization thing. Compute the matrix. The matrix will have X, Y, Z, and it's going to be such that its rank is going to drop. If I plug a point on that curve, the rank will drop. If it doesn't drop, if it's going to be an if and only if it doesn't drop, it's not there. And that's it. And after that, if you want, you can go and prove all the theorems you want about the maximal minus of the matrix, but my job is done here, right? What are the properties of these things? Well, the matrices that Laurent proposed, the entries are all linears in X, Y, Z, and the testing the rank is fast these days. And that's the principle of this. Why do you want to stop there and not continue? Is because it's very fast to test rank these days. And also with the reals, you can use all this singular value decomposition and all this factorization thing that actually makes the thing faster and makes the thing very feasible and usable. And is very well suited for a lot of problems in computer-aided geometric design. So this, and again, you may think that, you just do this because you don't want to do difficult, you just want to do difficult stuff. But to prove all these results, and you'll see this on Wednesday, there's a lot of very deep commutative algebra machinery that you need to understand, for instance, what kind of matrix you have to take, and which is this S that you need to go so that the matrix really works the way you want it to work. So it's not a trivial, this is not trivial, and it's not trivial math behind this, and also there's a lot of problems and a lot of challenges there. And the example that David gave today at the very end, the matrix of Nicholas Boldbol and Alicia Dickenstein, also is an example of these kind of things for surfaces. So I show you the example with curves, but this is done for surfaces. And it's also, it has been used and applied, for instance, for computing the intersection of a curve with a surface in a very simple way. So it's a very nice area. So you'll hear more of this about this on Wednesday when you come to David's talk. So now let me talk a bit about Swiss and Ries algebra, despite the fact that I'm just going to give you a warming up TAPA, very little, because you're going to have the rest on Wednesday. So on Wednesday, there's going to be a lot of information on Ries algebras and Swiss and the relationship with implicitization. I like this one because now it looks like David is looking at the TAPA, right? This is not healthy, I have to tell you. But, so I just give you an example. This is a very exciting area.
I think he's actually saying this is too small.
Yeah. So let me just show you this example that I always found fascinating. This is a paper by Soderberg and Chen, and this is like a dictionary. It says like this: the implicit equation of a rational quartic can be computed as a 2 by 2 determinant. here you have to assume that a rational quartic here is I give you a parametrization of a rational curve of degree 4, right? And very likely the parametrization will have 3 polynomials of degree 4. Well, so if the curve has a triple point, then one row is linear and the other is cubic. Otherwise, both rows are quadratic. So if you think for a while, if I want to compute the implicit equation of a rational curve using resultants, well, if it has degree 4 and you use a Sylvester matrix, you will have to deal with an 8 times 8 matrix. You can use Bezout matrix and you go to 4 times 4. Well, here, I mean, it's a 2 by 2, so it's already an improvement, right? And now it's telling you, okay, what kind of 2 by 2? And you have to think for a while that, well, I mean, linear plus cubic, I mean, the degree has to add up to 4 because the implicit equation will have degree 4. So you cannot do magic out there. So it's either linear plus 1 plus 3 or 2 plus 2. But the interesting thing is that what makes the difference actually is the singularity of the curve. Just, you know, this sounds like magic, and it would be great to have a dictionary like this for everything. But let me show you an example. So this is a quartic with a triple point. So here you have the parametrization. It's homogeneous coordinates, and this is the triple point. And that's the implicit equation. And you can see this determinant. I mean, the first row is linear. The second has degree 3. And this is related with all these moving curves, moving planes, moving lines, and everything that David was talking about today, and he will talk a lot about on Wednesday. So what's going on? So what the recipe didn't say, but if you read that paper, you'll see is that these coefficients here are actually come from some kind of pencils of curves. This is like a pencil of lines, and this is a pencil of cubics, and they follow this curve somehow. And if you plug them there and compute the determinant, you get that thing. And this is an example of a quartic without triple points. So then you have, because they're rational, they must have all the singularities they might have, but they're all double. And oh, I went back. Back. This is the implicit equation, and here you have the two equations of degree 2. That if you plug only the things with x in a 2 by 2 matrix, you compute the determinant and you get the implicit equation. So this is kind of a magic thing, and it was, I mean, it was very interesting that it appeared, and it triggered a lot of research in that area, a lot. For instance, later on, or it's very easy to see that this thing of 1 point with multiplicity 3, you can actually do it in general. If I have a curve of degree d with 1 point with all the multiplicity there, multiplicity d minus 1, then the implicit equation is always going to be the determinant of a 2 by 2 matrix, where one of these is going to be linear and the other is going to be of degree d minus 1. So this thing actually essentially started the whole, what's called the method of moving curves, which is, let's try, I mean, I'm going to, the philosophy of the method of moving curves is the following. And so this is something that it's not done yet. I don't know if it's going to be done. It could be a nice challenge for this century, but it is that the implicit equation of a rational curve should be computed as the determinant of a small matrix, where the entries are some moving lines, some moving conics, some moving cubics, I mean, you name it. And also, the more singular the curve, where I'm not going to precise what the more singular the curve is, because A, I don't know, I would like to know, but it should be that the more singular the curve, the simpler the description of the determinant is. And this is something that studied well. Let's start with the method, and I mean there are a lot of papers that have been produced. I mean several by Ron, by David, for curve, for surfaces, and we were all like, if I have how many moving conics, but they already have moving lines. But then if you have a moving line and multiply by x, you have a moving conic, and you don't want that because you already had it. So, but in general, we don't know. I mean, what we have to put there. We would like to have something like what they have for degree 4. I mean, it's always a 2 by 2 determinant, and it's either this or that. But in general, for degree 5, 6, maybe for those you know, but in general, for a given degree, we don't know that. And we were playing for a while, doing all these things, until David came and put some order. And in this paper, what David taught us was, okay, so you guys are looking at all these moving lines, moving curves, and everything, moving conics. So what you have to look is like just the kernel of this map. So here I have the parametrization, and I put an S here. So then the t's go to the t's, and then the x goes to essentially the values of the parameterization and the s. And all these moving curves are just homogeneous elements in the kernel of this map. And this map is, the image of this map is nothing but the Riesz algebra of actually this data, of phi0, phi1, phi2. So what you are looking is some kind of a presentation of the Riesz algebra. That's how Riesz algebras came into the picture. And it helped us a lot to put order in the things, because this was like having a lot of Legos. And we were just playing with them to build the matrix. The more compact, the better, but we still didn't know how many Legos of degree 2, how many of degree 3, and everything. How many are, once you have all of them of degree 1, 2, 3, can you put more? Do you need less? And I said, well, you just have to look at the kernel of this map, and in the new language, so the implicit equation should be obtained as the determinant of a matrix with some minimal generators, because now if you wanna be clever, you have to look at minimal generators of these things, and some relations among them. And this includes Sylvester, Bezout, and all the moving conics method and everything. And it would be great if we can prove this also, that the more singular the curve, where we still have to define what singular means, the simpler the description of this set of minimal generator. So this is one of the 21st century problems, which is computing minimal system of generator of this map for any parametrization. So we're working on that. Some results are known. David is going to report on them on Wednesday. And also, what I said about curves also can be translated to rational parameterization of surfaces and hypersurfaces, parameterization of varieties that are not necessarily codimension 1. And this whole machinery of Riesz algebras exists. But that's a problem that we would like to know. Think for a while that still what we don't even know, this is like the factorization of a number, right? I said, well, I have this number and I want to factorize it. So then you need at least the list of primes. In this case, the minimal generators of this kernel, they play the role of the primes. So we still don't know what the primes are. So we are at that step. And
Carlos, can I ask a quick question? So there's this paper of Bovie on determinal hypersurface.
Yes.
From 15 years ago. So the things that seem to be nice for curves, I thought that they got harder and harder as you go into higher dimension or something. I remember that he had some pretty strong restrictions on determinal hypersurface.
Yeah. No. Something that is true is that even when you can apply all this to surfaces, but you already start having problems there. Like simple problems like the definition of base locus and things like those. So. Anyway, don't miss Wednesday morning and afternoon, I was going to chat about. You're going to hear a lot. And again, this is an area where the problems came from this group of people in computer, people that were not doing algebraic geometry, and the answer to that actually involved non-trivial analysis and non-trivial tools on algebraic geometry. And the kind of tools that now we are using to understand these Riesz algebras, even at the very simple level, they're very, very deep, and it's not a very easy thing. So if you think that working on this application problem is going to make you miss some of the fun or good math or deep math, that's not true. There's a lot of very deep and interesting mathematics here looking in the background of all this. Okay, let's go back to the other changing the model of computation. I think that this is the Enigma machine that we have one in Madrid, I don't know why, but in a museum. As you well know, the Enigma machine is famous because it was the machine that was essentially deciphered by Alan Turing. But let's talk about probabilistic algorithms. And this is a nice paper written by all these Argentines. That's why the tapa here has some beef. This is Gabriela Jerónimo, Teresa Crick, Juan Savia, and Martin Sombra. So the title of the paper is The Computational Complexity of the Chow Form. And the Chow Form, if you don't know, you may think that the Chow Form is just a result. And this has been published in the Journal of FOCM 2004. So this is what in the abstract they say. Well, this is where the odd words start. we present the bounded probabilistic algorithm for the computation of the Chow forms, which are the resultants, of the k-dimensional components of a variety. The expected complexity of the algorithm is polynomial. Again, you see, it's polynomial. Which polynomial is great in the size and the geometric degree of the input equation system defining the variety. And listen to me. As an application, we obtain an algorithm to compute a subclass of sparse resultants whose complexity is polynomial in the dimension, the volume of the input set of exponents. Again, this is a thing when you think that, oh, this is just an article about something odd. Actually, they have applications, they get to compute sparse resultants, and they get good complexity. Now, let me show you a bit the math, or the main idea that goes there, and you'll see where all this probabilistic and all this complexity that we kind of look at it as if something coming from Mars is not that hard. I mean, it's actually math. It's just another language. So let's say I have a variety, so I have equations of a d-dimensional variety, which is in P to the n. And this is the thing. I will cut my variety with some general d hyperplanes. If this has dimension d, then if I cut it with d hyperplanes, in general I should have a finite number of points, right? And this is the probabilistic part, because this general, instead of just adding parameters and making the whole thing blow up, I just choose some, and I do, and I get my finite points. I believe this is also called some kind of a witness set. Yeah, so it's, well, what they call this a geometric resolution of my variety. Okay, so from this data, which I don't even need to compute, I mean, I just need something that codifies all that, I'm going to lift it to the Chow form of the difference between this and that is I have removed one equation. So I get something of dimension. This has dimension 0, this has dimension 1. And then I'm just going to iterate, and then I remove this one, I remove this one, I remove this one, and I get there. So this is the idea. It's simple, but it's very powerful, and actually it triggered a lot of results after this. So the star model of this computation is what they call straight line programs. Also this is a very recent paper that just appeared this year, which is called How to Compute Straight Resultants with Straight Line Programs. So first, let me explain to you what is a straight line program. Actually, it's not that hard to know. If you think for a while, it's a program that just goes in one direction. So it's a program that has no branches, no loops, no conditional statements, no comparisons, just a sequence of basic operations. So it's just pack, 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 pack. So you never have to ask whether A is larger than B or anything. And with this model, they actually got to compute. They could actually prove that this sparse resultant, the one that we did with Martin and also Alex Esterov did, the one with the exponent there, can be evaluated in a number of steps, which is polynomial in its degree, its number of variables, and the size of the exponents. But again, so you think the philosophy here changes. You're not computing the polynomial sparse resultant, the one that depends with all the coefficients. You're evaluating it, which means they give you the concrete polynomials, and you're going to give me the number, which is the sparse result. And then they design a probabilistic algorithm of this order of complexity to complete a straight line program that evaluates it within this number of steps. In general, straight line programs are very good for evaluation. But yeah, this is the kind of papers that when you look at them, you think, oh, I won't understand anything because this language is obscure. But I mean, there's some words that are odd. But like, for instance, this whole thing of geometric resolution versus witness set. And they're the same thing. Just have different names. But the funny thing in both cases, in this paper and the previous one, is that to do this iteration, they actually use Poisson formula for the resultant, because it's very well suited for recursions. And so if you actually, and this is funny because sometimes you think, well, Poisson, he started saying, well, this whole Bessel thing is really uncomplicated, and he did his own thing. And sometimes you think, why are you going to do this if someone else did it? Or why are you doing this thing which is very complicated when this has already been done in a simpler way? Well, first of all, what is simple and what isn't is we can discuss about that. But second, the more tools we have, the better. In this case, Poisson formula from a computational point of view is very good. because you can do iteration, you can change dimension, and it goes very well, and it behaves very well with respect to Newton's method. And that's the thing that makes all the thing go fast. So the main ideas in this paper of Gabriela, Geronimo, and Juan, they use these straight line programs. They use this geometric resolution again, and then Newton-Hansen lifting, and also something by the approximations, and they go through. So it's, you see that these are kind of results that are recent, and also, it means that also there was nothing as good as this before, because they're quite very good. So this is another real model, which is the Bloom-Shub-Smale machine, which is complexity over the real. So what you do here is you're not going to look at the complexity of the size of your numbers. So you can just store arbitrary real numbers, and with that you just compute rational function, for instance, at unit cost. And this model, what do you think? Are you cheating there or not?
Well, there's no computer.
Yeah, well,
It's not going to help you compute anything.
it's not going to help you with your
Except for telling you some things are hard.
yes, yeah.
It isolates the hardness.
Yes, it's true. But some of the first paper, the computational complexity of the Chow form, they actually use this model for their model of computation, and then they go through it. But it's there, and there are a lot of problems also in this size. So, for instance, this is one of them. That is, instead of I give you a polynomial, let's say with integer coefficients, so we're not using this BSS model, and I don't want all the roots. I just want a small approximate root, and I want it fast. Okay, so I'm going to go back. The game is, I'll give you the polynomial with integer coefficients, and I want a small approximate root fast. Fast, we all know what it means. Small, you may say, I want something that it's a rational number, it doesn't have a lot of digits. Let's say that is small. And now let's see, what is an approximate root? Well, an approximate root should be something that the Newton method works well there. Okay? So if let's say this is my approximate root, and I know because Newton method, let's agree that it's fast, and in 2 or 3 seconds I'm going to get some good approximation of the root. So that is an approximate root. So that seems to be like a silly problem, because at least in one variable, the set of roots that are not good with respect to approximation is exactly the zeros of the derivative of this polynomial or something. It can get complicated. And design an algorithm to do this is not easy. And this actually led us to Steve Smell's 17th problem that was posted in '98. And the problem is there an algorithm which computes an approximate solution of a system of polynomials in time polynomial on the average in the size of the input? So this was one of the problems that Steve Smell proposed for this century. And this, among others, the Jacobean Conjecture was there. And there was a lot of work done in this century to solve that. In principle, there were a sequence of papers by Carlos Beltrán and Luis Miguel Pardo, where they first provided a probabilistic algorithm for that thing. Then they shown that, average, it was kind of fine. And then later, Felipe Kukier and Peter Burgiser, they actually shown that this algorithm was way better than they expected to be, but yet the problem wasn't solved completely until last year. When, are you follow me? Yeah. PLRS, and there's a whole tapa dedicated to him. If you have been to any conference in the area last year, you probably have seen him as a main speaker there. He was at SciMAG, he was at Mega, he got an award at SciMAG, and in this paper, a deterministic algorithm to compute approximate roots of polynomial systems in polynomial average time, he solved Smell's problem. And again, as I said, these are going to be the tapas. I'm not going to tell you what he did with respect to all the others, because here it is a serious problem, and actually the solution is not trivial. I guess I need to talk about the homotopies yet, but I'm going to see them in depth tomorrow, so I'm just going to see very few words. The typical thing is that you just start with this is the system that you want to solve, and you just start with some good and easy system, and then you track them with some kind of homotopy. And the way you are correcting this is, I mean, you chase the roots of this system by using Newton method, and you can keep track and go on. I mean, you'll hear a lot about this tomorrow. And but with the numerical algebraic geometry, which is what you use to do the things, you can compute very fast a lot of things. You can compute the components of a variety, the multiplicities, the decomposition and the dimension. So this is, again, something that you can compute in a very fast way. I mean, we won't get the nice representation in the sense that, I mean, if you have something parametrically, probably you won't get an answer that is parametrical, but if you have something concrete, you can do all this in a very nice way. And then there are implementations of this. So time is up, so I mean, what things I haven't said about this, not in the menu today, you don't get upset with me if I didn't talk about your favorite topic or what you think that's going to be used in this century. But you may think that we were eating tapas, right? Well, then it comes a meal. So this is what you may think that the meal, which is I didn't talk about, like this paella, you would never get paella as a tapa. So it's a meal. For instance, something that is a very hot area these days is this differential elimination theory, and also difference. I mean, you replace derivation with some kind of automorphism. It's a very hot area. There are very recent results on differential Nullstellensatz, differential resolvents, differential resultants, and a lot of people working on that. Real elimination is at the core of a lot of things, I mean, there are a lot of people here working on that. I mean, for instance, generalizations of the card rules and things like those are being very active these days. Applications, of course, we are all here about that. And implementations also, which is very important. Because, I mean, we're doing this whole effort because we want things to be computable, but then also we need to compute them. We need to be able to compute them, right? And sometimes we are being paid for doing computations, so implementations. There's going to be a session on software tomorrow afternoon here, so you will see something about that. And there are a lot of things more that I haven't put here. And as I told you, it would be great if we meet all together at the end of this century to see whether, to see how accurate this was. But anyways, so the conclusion is, I hope you're hungry by now. So this 21st century has been driven, I will be driven by, of course, the applications, and also by fast and efficient computations. And this is something that maybe you are not totally aware of it, but I mean, we get happy when we can compute things, we get happier when we can compute them faster, and a lot of things are taking us in that direction. We are somehow, essentially it's modeling, it's shaping where our research is going. And there are very interesting challenges and problems here. And of course, we need the help of all of you. I'm very happy to talk to any of you about any of these things as much as I know about this, or to give you direction. But in any of these things that I was presenting, there are a lot of problems, a lot of challenges, and we definitely, I mean, we would like a lot to have your help and the help of everyone else. So thanks a lot. And if you have any questions or comments?
Your tap is filled everybody up.
Pardon?
Your tap is filled everybody up.
Yep.
So you mentioned about changing the model of computation. You didn't say anything about quantum computing.
Oh.
Anything about that?
Well, I know that quantum cryptography now is getting quite hot, but didn't hear anything about yet quantum elimination or things like those. But definitely that's something that's also going to be triggering us. I was planning to say something, but I didn't want to say anything inappropriate. Well, not inappropriate, that I don't know that much yet. But
I think one thing, so quantum computing is not just faster computing.
Yeah.
There are certain things that behave well in a quantum computer.
Yeah.
And certainly, I don't know if people know anything about solving systems, if they do or not. That is an open area.
And so the one thing I know is there's a company in Canada, D-Wave, that makes what they call an adiabatic quantum computer. And what it does, it's working in a certain polytope in dimension 24, that's a certain energy functional, and it's trying to pick a facet.
okay.
And basically the quantum stuff picks the facet, and that's somehow part of the computation.
Okay. That's That's the first time I hear quantum computation with something related to computational algebra geometry.
But for example, they wanted to know how many facets did this polytope actually have, and then they had to ask somebody with a regular computer to actually count the number of facets.
So still they need help from the classics. Yeah. I know that there is already some papers on quantum complexity or something like that, but for me that is what Frank qualifies as cheating or as writing one other paper. All right, well, thanks again, and